This lecture is part of the online course on multivariable calculus, and we're going to solve 3 examples that show how to prove that the limit does not exist. I'm going to start with a note. To prove that the limit exists, we can use epsilon delta definition, or we can use continuity. And how? Continuity. And how? We say that the limit of f of x and y as x and y goes to the point x naught, y naught is equal to, it exists actually, and it's equal to f of x naught, y naught if the function f is continuous. So that's how we use continuity to show that the limit exists. Then to show that the limit does not exist, so to prove that the limit does not exist, we can check all the path that passes through the point. So check the path through the point x naught and y naught. And so you see, for example, if this is the point x naught, y naught, and then the curve, for example, c1 passes through that, and the limit of the function as x and y goes to the point x naught, y naught along the curve is equal to L1. And if we have another curve C2 that passes through the point x naught, y naught, and the limit of f as x and y goes to x naught, y naught along C2 is equal to another number L2, then the limit does not exist. Since these L1 and L2, if they are not actually equal to each other, then the limit does not exist. If L1 and L2 they exist, you can they are the same, you can check other path. Okay, but to prove that the limit does not exist, just find 2 different L1 and L2. Let's look at an example. The limit of the function xy over x squared plus y squared as x and y goes to 0, 0. What is this limit? Okay, so as you see, the function f is not continuous at the point x naught, y naught. Okay, so f is not continuous at 0, 0 because the point 0, 0 makes the denominator equal to 0. Okay, that's why it's not continuous. So now I assume that the limit does not exist, but let's check. I'm gonna approach the point 0, 0 along x-axis. Okay, so along x-axis, actually y is equal to 0. So I'm gonna plug it into the function. It's x, and then y is equal to 0. So plugging in there, I get 0 over x squared plus 0 squared, which makes it 0. And the limit of this function, f of x and 0, which is 0 as x goes to 0, it's equal to 0. So I found the value for L1. I'm going to approach the point along the y-axis. Along y-axis, x is equal to 0. So the function would be 0 and x. Actually, 0 and y. It's along the y-axis. So I'm going to get, still, it would be 0 times y. So I get a 0 and then 0 squared plus y squared. That's why I get 0. Then again, the limit of 0 and y as y goes to 0. This function is 0. That's why I get 0. Perfect. Let's check another path through the point 0, 0. I'm going to pick x equals to y. Okay? Then I'm going to plug in for any y in the function. I'm going to plug in x. This is the value of the function along this curve. Okay? So I get x times x squared, and then I get x squared plus x squared, which would be 2x squared. So I get 1/2. Now, the limit of f of x and x, this function is actually 1/2. As x goes to 0, it's 1/2. Okay? As you see, I have a problem. I got 0 and I got 1/2. So I can say that f does not have a limit. Does not have limit at 0, 0, because I got two different values when I approaches the same point. So let me show it to you, the graph. So this is x y over x squared plus y squared. As you see the shape, we have a hole in at the origin. Okay, so that's why the limit does not exist. It goes up and down in one direction, and it's equal to 1/2 in another direction. X equals to y would be this line in here. Let me move it. So this is x equals to y, and as you see, the value of the function along x equals to y is equal to 1/2, but along the x-axis and y-axis it's 0. That's why we get a different values for the limit. Okay, let's look at another example. I'm gonna find the limit of x cubed y over x to the power of 6 plus y squared as x and y goes to 0, 0. What is this limit? So again, this function is not continuous because it has a polynomial over a polynomial, which is good, but at 0 over 0 we have a problem. We get a 0 on the denominator. That's why the function is not continuous. So now we want to prove that the limit does not exist. I'm gonna approach 0, 0 along x-axis. Along x-axis, y is equal to 0. So I'm gonna put f of x and 0. I'm gonna find out the limit. It would be the limit f x and 0. I get a 0 over x to the power of 6 plus 0. So I get a 0 over x to the power of 6. As x goes to 0, this is the function 0. So that's why I get a 0. Now I'm going to approach the point 0, 0 along the y-axis. Along y-axis, x is equal to 0. That's why I get the limit of f of 0 and y as y goes to 0. So you see, basically y and x are getting closer to 0. Now I find the value of the function at the curves that I'm looking at. So x is equal to 0. I get 0 over 0 to the power of 6 plus y squared. As y goes to 0, this is the function 0. Okay, so the answer would be 0. The function here is 0. Let's check along, for example, you can check along x equals to y, and then we get the limit of f of x and x as x goes to 0. This would be what? This would be x to the power of 4 over x to the power of 6 plus x to the power of 2. I'm going to factor out x to the power of 2. As x goes to 0, I'm going to simplify these two. I get x squared. So I get the limit of x squared, x to the power of 4 plus 1. So it would be 0 over 1, which is still 0. Good. Let's check y equals to x cubed. Then f of x and x cubed, as x goes to 0, it's equal to what? Let me find the value of the function. It would be x cubed, and then instead of y, I'm going to put x cubed. So it would be x to the power of 6, and then x to the power of 6 plus, and then I get x cubed to the power of 2. To the power of 2 as x goes to 0. This is the value of the function, and as you see, I get 2x to the power of 6, and the denominator, these two would be cancelled. I get 1 over 2. Okay, now I have a problem. I got a 0, and in another line I get 1/2. That's why the limit does not exist. This is the notation for saying that the limit does not exist. Let me show it to you, the graph. Okay, this is the first graph. Now this is the graph of this function. You see? Along the x-axis and y-axis, so this is x-axis, this is y-axis, it's equal, the limit is 0, but along y equals to x cubed, it's equal to 1/3. Yeah. Y equals to x cubed is something like this, and it goes up and down. That's why the limit does not exist, you see? And 0, 0, it's not even in the domain of the function. That's why we get it like that. Okay, let me give you one more example. What is the limit of x squared minus y squared over x minus y as x and y goes to 0 and 0? So this function, again, it's not continuous. It's just because 0, 0, it's not on the domain of the function. We have a denominator at 0. But you see, I can write this function as this: x minus y, x plus y, and I have x minus y on the denominator as xy goes to 0, 0. I can cancel out these two. I left with x plus y, and now I have the limit of x plus y as x and y goes to 0, 0. Now this is just a polynomial and it's continuous. That's why I can plug in the point into the function and I get 0. So the limit for this one actually exists. Now let me show it to you, the graph of this function. You see, this is z equals to x squared minus y squared over x minus y. It's a plane. Actually, it's z equals to x plus y plane, but the line x equals to y is removed. It's just because it's not in the domain. But as you see, if we approach to 0, 0, the limit exists, just because at every curve that you choose to go to 0, 0, you get 0 as the limit, although the function has a hole on the 0, 0, as you see, or actually any point on the line x equals to y, it has a hole, but the limit exists.